Hello everyone, my name is Julian, and it is a pleasure to present our work at the International Joint Conference on Neural Networks. I am a researcher in University Federal Bahia with experience in deep learning applied to medical image analysis. Now I will present our paper entitled SESAN-KAN Simultaneous Estimation of Sex and Age from Panoramic Radiographs, which proposes a multitask learning approach applied to the analysis of dental images. Developed in collaboration with Igor Borja, David Lima, Márcio Júnior, Patrícia Cury, and Luciano Oliveira. Our presentation will be divided into the following topics. First, we will give a brief introduction contextualizing the problem. Next, we will address the proposal for simultaneous sex and age estimation, followed by the methodology used, including technical details. Afterwards, we will present the experimental analysis and the results obtained. Finally, we will discuss the final considerations and future perspectives. Identifying individuals is a critical need in a variety of situations, such as adoption cases, humanitarian contexts involving refugees, and especially in forensic medicine, when there are bodies in an advanced state of decomposition. In these scenarios, panoramic radiography emerges as a useful tool because it is non-invasive, non-destructive, and widely available in dental offices. Conventional methods for estimating sex and age, despite being widely used, have important limitations. They are highly subjective, require specialist experience, and are not easily scalable to large volumes of data. In this context, the use of deep learning techniques becomes promising, as it allows the analysis of multiple anatomical characteristics in an automated manner, with greater speed and less influence from human bias. Several studies have only explored the sex classifiers in dental radiographs. Milosevic et al. 2019, for example, observed that the performance of the models decreased as the age of the patients increased, mainly due to the scarcity of older samples. SESAN-KAN et al. 2023 showed that variables such as resolution, sex, and age influenced the performance of the model, with better results obtained for women over 16 years old. Other studies, such as that of Hugaz et al. 2023, focused on pre-trained models from the EfficientNet family. Other studies have also investigated estimation of age. Heinrich et al. 2024 developed a custom CNN aimed at integration with human identification systems. Milosevic et al. 2022 explored networks with attention mechanisms, and Liang et al. 2023 tested advanced architectures such as ConvNext v2, Vision Transformer, and EfficientNet on a set of over 7,000 radiographs. In the field of sex and age estimation, Milosevic et al. 2022 explored the multitask approach but obtained inferior results to single-task models. He et al. 2024 used cephalometric radiographs focused on children and adolescents aged 3 to 18 years, and Prado et al. 2024 successfully implemented EfficientNet v2L with dynamic weighting of the loss function, outperforming conventional models. We introduce here a simultaneous estimation of sex and age in a multitask architecture trained with the SESAN-KAN. Our network integrates the self-supervised pre-training of VIT with the mask autoencoder optimized through a CAN and a dynamically weighted adaptive loss function that adjusts task weights in real time, increasing the learning efficiency during training. The SESAN-KAN model consists of two main steps. First, a vision transformer-based encoder is pre-trained as a masked autoencoder, allowing it to learn relevant visual patterns without the need for labels. In the second step, the image is divided into patches and processed by this encoder. The resulting latent vector is then passed to a CAN, which acts as a decoder and generates age and gender predictions. This combination leverages the extraction power of VT and the flexibility of CAN, merging the two tasks into a multitask model. For pre-training, we used the mask autoencoder, a self-supervised technique. In this figure, we see the example of reconstruction of a dental radiograph. From left to right, the original image, the image with 5% of the pixels masked, and finally, the reconstructed image. This technique allows the network to learn relevant patterns of the tooth structure without the need for labels. In our approach is the use of the Kolmogorov-Arnold network, or simply CAN. This architecture is inspired by the Kolmogorov-Arnold theorem, which guarantees that any continuous multivariate function can be decomposed into sums and compositions of continuous univariate functions. In practice, this means that CAN replaces the traditional linear weights of neural networks with trainable, nonlinear, one-dimensional functions. This change brings greater capacity to represent complex relationships, which is essential when dealing with variable anatomical structures such as bones and teeth. Another key component of our model is the dynamic logarithmic weighted loss function. In multitasking models, it is common for one task to overwhelm another during training. To avoid this, we use a strategy that automatically adjusts the weight of each task based on the learning rate. When one task learns faster, its weight is reduced, allowing the other to receive more attention. This dynamic adjustment ensures more balanced training, resulting in better performance on both tasks, as verified in our results. The pruning process involved training a preliminary model on the dataset of 7,666 images using 5-fold cross-validation. After running the best model obtained from cross-validation on all images in the dataset, the resulting predictions were analyzed to identify outliers, with residual analysis performed by age group. The resulting box plot allowed visual inspection and subsequently the removal of images with residuals above the third quartile. Some examples of images removed after visual analysis. A. The image is labeled as 6 years old but does not show deciduous teeth, indicating possible inconsistency. B. Radiograph without adequate coverage of the oral and maxillofacial region. C. Blurred head radiograph without highlighting the oral and maxillary region. The eliminated images included those of low quality, instances with inconsistent age labels, radiographs that failed to meet the criteria for a panoramic image, and those exhibiting excessive noise or significant loss of contrast. After the pruning process, the table summarizes the pruned panoramic radiograph dataset, detailing the sample distribution across age groups for male and female patients. The pruned dataset included patients aged 1 to 90 years, with 4,180 images, 60.56% of female patients, and 2,917 images, 39.45% of male patients with a mean age of 32.47 years. The implementation was carried out using PyTorch. Models were trained with a batch size of 16 on a computational environment comprising a NVIDIA 4070 GPUs with 12 GB of VRAM, 16 GB of RAM, and an AMD Ryzen 7 processor. As regularization strategies, a weight decay of 0.01 was used to mitigate overfitting by penalizing excessive weights. To assess the performance of SESAN-KAN, we compared it against two alternative MTL methods, EfficientNet V2L and ViTL16 MAE. plus MLP, which uses the same base architecture as SESAN-KAN, but substitutes the CAN layer with an MLP. All methods were trained independently using 6,152 images for training and 1,245 images for testing, following a 5-fold cross-validation strategy stratified to maintain proportional sex and age distribution across the dataset. When including pre-training with MAE, there was an improvement in age error and F1 score. With the addition of the CAN layer, the gains were more significant. Age error decreased by 0.5 years and F1 score increased by 7.5 percentage points. These results show that the integration between VIPS, MAE, and CAN offers a more accurate solution for the simultaneous estimation of sex and age. For a more detailed analysis, we evaluated the sex classification tasks separately. The model achieved high overall accuracy even across different age groups. The model obtained an overall F1 score of 94.2%. The best performance was observed in the intermediate age groups, especially between 31 and 40 years old, where the model obtained F1 scores of 99% for female samples, while the best performance for male samples was in the 71 to 80-year-old range, with an F1 score of 97.7%. In contrast, performance was slightly lower in the extreme age groups, particularly 1 to 10 years and 81 or 91 years, where the combined F1 score was 75.1% and 83.9%, respectively, the lowest values among all groups. Sex classification accuracy followed a pattern distinct from age estimation, with lower performance in the extreme age groups, children 1 to 10 years and elderly over 80 years, and higher accuracy in adults, corroborating previous studies. However, among children, the lower efficiency can be attributed to less pronounced morphological differences due to hormonal influence, with more pronounced changes after puberty, especially in girls who completed this development earlier. On the other hand, at older ages, the model also faces challenges, especially due to factors such as physiological changes associated with aging, such as the masculinization of cranial features in women after menopause and the loss of bone strength in men. Moving on to age estimation, this graph shows the relationship between actual age and that estimated by the model. SESAN-KAN demonstrated a high correlation between the estimated and the observed ages, with an R2 of 92.0%. The concentration of points close to the red line indicates good accuracy. We observe greater dispersion at older ages, which suggests more variability in predictions. This is due to the lower presence of specific dental markers in older people, making it difficult to accurately estimate based on dental radiographs alone. To complement this analysis, this box plot graph shows the distribution of absolute error in age predictions for different age groups, highlighting trends and variations in model errors according to age. A significant incidence of outliers is noted in the 11-20 and 21-30 age groups. Furthermore, from the 41-50 age group onward, there is a sharp increase in the interquartile range, indicating an increase in the variability in prediction errors. This increase in error can be attributed to a combination of factors, including data bias and the absence of specific dental markers at older ages. This behavior reinforces an important point. The model's accuracy is more consistent in young and adult age groups, while in older individuals, performance becomes more sensitive to individual variations. This is due in part to the reduction in specific dental markers. this challenge has also been observed in previous studies, reinforcing the need for a more balanced data set and techniques that incorporate other physiological indicators relevant to these age groups. However, applying MTL in forensic dentistry over panoramic radiographs comes with challenges like balancing tasks of varying complexity and accounting for anatomical variations across different age groups. Additionally, the scarcity of large, well-annotated datasets and the need to model intricate interactions between dental features further complicate implementation of MTL-based architecture. To address these challenges, we introduced the integration of the VIT architecture, CAN layers, and a dynamic logarithmic weighted loss for multitask balancing. This led to the development of SESAN-KAN, which achieved a mean absolute error of 3.39 years in age estimation and an F1 score of 94.2% in sex classification. As future work, we propose investigating the generalization of the model in different populations, as well as the application of interpretability techniques to clinically validate the learned patterns, and finally, develop clinical impact studies to quantify the potential benefits in terms of diagnostic time, error reduction, and operational costs. We would like to thank the National Council for Scientific and Technological Development, CNPq, which supported this research through Luciano Oliveira. Some of the references used in the article